our next speaker is going to be Professor Dr. Syed Khalid Saifullah. And he's going to talk today. You would have the introduction from the yesterday activity, and he's today because our concept of the day is the innovative research and industry academia linkages. So he is also the lead member of BZU Core Engine Design Group. And his area of interest, the research, are computational fluid dynamics, heat transfer, optimal shape design, speech production, combustion simulation, multi-body dynamics, and internal combustion engines. So he would talk about the how to take up interdisciplinary and multidisciplinary research in mathematics. So Dr. Saifullah, please, if you can share your screen for the talk. And also, sir, if you can please turn your camera on.
Yes, let me please. Bismillahirrahmanirrahim. Allahumma salli ala Sayyidina wa Mawlana Muhammad wa ala ali Sayyidina wa Mawlana Muhammad. Respected audience, the title of my today's talk is Interdisciplinary and Multidisciplinary Research in Mathematics. The objective of the talk is to demonstrate to the audience that only mathematics can play the central role in the unification or integration of different disciplines. The outline of the talk is introduction, rationale behind this talk, abstract nature of mathematics for quite easy interaction with any other discipline, multidisciplinary and interdisciplinary research, and conclusions. Okay, first of all, let me a bit explain the terminology relevant to disciplinarity. Usually, there are 5 different terms: interdisciplinary, cross-disciplinary, multidisciplinary, interdisciplinary, and transdisciplinary. Let me explain a little bit. Interdisciplinary is working within a single discipline. For example, we are working on purely mathematical problem, then we are working on the basis of interdisciplinary. Cross-disciplinary, when we work on a project, and we just do our share. For example, there is a physicist, a mathematician, and chemist working on a project. Physicist will do his work related to physics. Mathematician will do the work related to mathematics. Then such type of collaboration will be called cross-disciplinary. And multidisciplinary, what I have explained earlier, that is multidisciplinary, in which every person works according to his own knowledge discipline. In the cross-disciplinary, a person of one discipline looks at the other discipline from his own perspective. For example, if I look at physics from a mathematical point of view, or a physicist looks at chemistry with his physical point of view, then it will be a cross-disciplinary collaboration. Then there is an interdisciplinary. This is the collaboration in which the knowledge and methods of different disciplines are integrated, they are synthesized, harmonized, and a single coherent object is approached. Single coherent production is obtained. And in the interdisciplinary collaboration, usually the different disciplines retain their identity up to a certain extent, but they are not maintaining their identity on a 100% basis. And in the transdisciplinary collaboration, every discipline loses its own identity, and there is a single piece of intellectual work in which all disciplines work together without caring others to which discipline they belong to. And next is multidisciplinary and interdisciplinary area. This is just an introduction that how mathematics is penetrating other disciplines. You can see these terms very frequently. You will see mathematical physics, mathematical chemistry, mathematical biology, mathematical economics. You will see computational physics, computational chemistry, biology. Even in MIT, they are working on computational law, in which they are mechanizing the legal arguments. They are going to design a logical framework to organize the law, the legal reasoning and legal regulations. And we have the computational linguistics. Mathematics has its application in languages. Mathematics has its application in modeling human behavior. So we have a computational psychology. So there is a lot of there are a lot of opportunities for the mathematicians to interact with other disciplines. Likewise, we have I have just for example, I have taken two situations where the mathematics has collaborated right from the beginning. There is a mathematical data science group in the Oxford University, and the Mathematical Institute of the university is a founding mathematical partner of this mathematical data science group. And the members of this data science group are also leading for large data science initiative, Center for Topological Data Analysis. So we have here the role of mathematician in the data science right from the beginning. There is a lab of mathematical chemistry in US that was established in 1984, and the research at the lab of mathematical chemistry focuses on mathematical methods for predicting toxicity of chemicals and modeling of metabolism. LMC is a leader in software development for ecotoxicity assessment and chemical databases. LMC team members have expertise in chemistry, biochemistry, physics, mathematics, and software development. And the research areas we are working in are molecular modeling, environmental fate and ecotoxicity, human health hazard, and metabolism. So we can see here how the people from different disciplines work together in the form of a team. And I have just given some examples of multidisciplinary journals that involve mathematics. For example, Journal of Mathematics, Mathematical Chemistry, published by Springle. There is a Journal of Computational Sociology, a journal namely Mathematical Biosciences and Engineering, and there is a Journal of Interdisciplinary Mathematics as well. Okay, we have now the rationale why we, as a mathematician, looking for multidisciplinary and interdisciplinary collaborations. Mathematics, there are well-known quotations for the mathematics. It's a language of science. It's mother of all sciences. It's a science of all sciences and art of all arts. And it's a unifying science. And the philosophers say that the creator of the universe is a mathematician. So you see, if we look at things in the universe from mathematical point of view, we find certain disciplines, we find structures, patterns in all the universe, and obviously the patterns and structures are governed by mathematical rules, mathematical principles. So it's quite easy as compared to other disciplines to understand the universe in terms of mathematics. Another reason for mathematics is it has abstract nature without any physical or other interpretation. I will talk on this issue later. And there is another point, foundation of truth in mathematics. In mathematics, we take the thing true only on the basis of logical reasoning. Once a concept is proved in mathematics, then it cannot be false in future at any time. While in other disciplines, the truths are established on the basis of experiences, experiments, and experiences and experiments carry errors, and their theories developed on the basis of experiments or experiences may get false in future. So that's why only mathematics has the ability to provide foundation to other disciplines, because the truth that has been once established in mathematics cannot become false in future at any time. Now, there is a very simple expression y is equal to f of x. We all know this expression. This is quite abstract information expression, but it has a lot of background, lot of applications in this real world. We know this relation is this is a relation between two variables. We call it a function. Y is a function of x, and we know in the whole calculus we study expression like this without mentioning what x or what y will be. And we study its mathematical properties, we study its continuity, differentiation properties, integration properties. We optimize the function, find its extreme values. We sketch, we study its behaviors like monotonicity, concavity, convexity, its oscillatory behavior, its asymptotes, its vibrational behavior. So we have a lot of situations where this function can be used as a model. And this is the strength of mathematics, that when we give some sense to the variables x and y relevant relative to a certain discipline, all the mathematics that has been studied during this for this equation will be applicable to that discipline. And when we change the interpretation of these variables, the whole mathematics of this function will be applicable to that discipline. So this is the abstract nature of this mathematics, of this expression, that makes it applicable to every other discipline. May it be physics, chemistry, economics. You saw in the previous slides that we have applications of mathematics in languages as well, in sociology, in psychology, anthropology. Everywhere we find applications of this expression. There is much explanation background of this expression, but because of shortage of time, I will not go into the detail. The people who have studied calculus, they know applications in the these functions are used as models, and these functions sometimes we know these functions usually represent a certain process, a certain type of relation between two variables, and sometimes we know this relation and then we study its behavior in the light of this relation, and sometimes we don't know the direct relation between these two variables. Rather, we have some indirect information about this function in the form of a differential equation or an algebraic equation or in the form of an integral equation, and by solving that equation we get this relation and we interpret our results according to the specific discipline. So the whole real analysis or calculus is here with this function, stands with this function. If x and y are scalar, then this is a relation between simply two variables. If x is a vector n tuple, then y is a function of n variables. If x is a vector and y is a vector, then this is a vector function of vector variable. So we have many interpretations of this expression. This is a simple neural network model. I will not go into much detail, but I just want to mention how abstract it is. You know, this is a question matrix A. This is our column vector. When we multiply this equation with this vector, we get this vector y1, y2. And you see, if you multiply this matrix, this column will have on left side a linear combination of x1, x2, x3 with these coefficients. And first equation will give this, make this linear combination equal to y1. And when we take multiply the second row with this column, we have another equation that will On the left side, there will be linear combination of these x's, and on the right side, we will have y2. So these x1, x2, x3 can be regarded as inputs, and y1 and y2 can be regarded as outputs. Now, if you have some known data, you have certain combinations of inputs and outputs. You know, if you give this input, you get that output. If you give another input, you get another output. You have a certain input-output data. You can use that data to estimate these A's, this matrix A. Okay, and we can estimate these A's on the basis of least square approximation. After having an estimation of these A's, this matrix A will become a representative of the relation between this input data and output data. Okay, so first of all, we have some training data on the basis of which we estimate this matrix A. Then we have another test data where we know input and output, but we use these inputs and compute outputs using this matrix, and then compare our computed output with our known output. In this way, we can get how accurate this matrix has been estimated. When this matrix passes the test data, it produces outputs that are near to our known output data as per our tolerance. Then we accept this matrix as representing the system from which we obtain this input and output data. And we can say that now, whenever we give another input whose output we don't know, we can use this matrix to generate the output, and this is artificial intelligence. That you didn't know output, but using this input, any input of your desire, you generated an output, and that output will resemble your expectation. So this is how artificial intelligence works. And now you see here we haven't mentioned what in these inputs and outputs belong to which system. This is purely mathematical work, and we will have a certain procedure that can be applied to any collection of training and test data and any desired output for a given input. So that's why this is how mathematics work in an abstract way, and it can be applied to any data set relating to any type of discipline. Okay, now you know the people who have studied partial differential equations, they know classification of the partial differential equations of second order. We call them elliptic partial differential equations, parabolic partial differential equations, and hyperbolic partial differential equations. Now, in parallel to this classification of PDEs, we have a classification of problems, namely equilibrium problems, evolutionary problems, and propagation problems. Now, equilibrium problems, they represent a situation in which there is something moving, but that transportation is in equilibrium. For example, if there is a room, there is an entrance door and there is an exit door, and the number of people per unit time entering into the room is equal to the number of people exiting the room, then we can say that the number of people in the classroom, they are in equilibrium. With the passage of time, their population is not changing. Now, if we have some rule that governs the rate of entrance and rate of exit, we don't know exactly the number of people, but we know the rate at which people are entering and the rate at which people are leaving. And then, with the help of that rates, we can formulate this problem in the form of a partial differential equation that will be elliptic partial differential equation. And you see, this is one example of equilibrium problem. You can have such problem in every discipline. For example, you have a rod that is being heated on at one end, then that is being cooled at the other end. And if after a certain time, you will see that the temperature at any point of the rod is not changing. It means the heat that is entering from the hot end is balancing the heat leaving from the cold end. So the heat transportation becomes in equilibrium position, in equilibrium situation, and such type of transportation of heat, transfer of heat, will be modeled by elliptic partial differential equations. So we have a general classification of the problems in terms of equilibrium problems, evolutionary propagation problems, without mentioning any discipline in which these phenomena are occurring. So this is the strength of mathematics. If you know to solve an elliptic PDE, for example, Poisson or Laplace PDE, then you can solve a lot of problems of other disciplines. Just your one solution will work in all the other disciplines. Likewise, evolutionary problems, these are actually time-dependent problems in which a system a process starts with from an initial state, and with the passage of time, its state changes. We say that it is an evolutionary situation, and such situations occur in every discipline of life, may it be social sciences, may it be physical sciences, natural sciences. Everywhere these processes occur. For example, market conditions, they are always time dependent. They are not static. They are not in equilibrium, but these are changing with time. So the market condition may be more considered as evolutionary problem. And if in the market the demand and supply are in balance, then there will be equilibrium. There will be a steady state in the market, and the prices will not change. Prices will be stable, and balance in demand and supply represents stability in the market, and that situation will be represented by an equilibrium problem of mathematics. The third category of the problem is a propagation problem. That is, we have wave phenomena where waves, we create a disturbance at certain location, and that disturbance travels, and that the transportation of that disturbance is modeled by wave equation, by hyperbolic partial differential equation, and we can have its application almost every field of every real life field. For example, we have acoustic waves. Our sound travels in the form of waves. We have electromagnetic waves. We have fluctuations in the market. That is also, if there is a fluctuation at in Lahore, for example, a big city like, for example, Karachi is considered an industrial hub of Pakistan. If there is some sort of fluctuation in Karachi, that fluctuation will travel in other cities of the country. And then that fluctuation may be modeled with the help of propagation problems. This is a Poisson equation. This is actually a model elliptic partial differential equation. And as I mentioned earlier, this represents deformation in a bar or in a beam. It can represent electrostatic charge problem. It can represent a steady state fluid flow problem. It can represent steady state heat transfer problem. It can represent steady state mass diffusion problem. Actually, this is a diffusion equation. Diffusion means whenever there is a difference of concentration of a certain property, then naturally that property travels from higher concentration level to lower concentration level. We know if we have a steel rod, one end is at higher temperature and the other is at colder temperature, then the heat will automatically flow from hotter end to colder end. Likewise, if we have, the water flows downward from mountains, that is because of the height difference. So this difference of height provides the potential for the water to move. So these Poisson equations, this models all the processes involving steady state diffusion. We have another equation that is a well-known convection diffusion reaction equation. The first term of this equation, this shows time rate of change of some property U. The second term, this shows convection of the property U. Convection means when a fluid moves, while moving, it carries some property with it, like when we are sitting under a fan, ceiling fan, if the fan is not running, we feel hotter. But when we switch on the fan, we feel colder because uh, the fan pushes the air. While moving this air, it absorbs heat from our body and then passes on. Then fresh air comes to our body, and this process continues. In this way, through the motion of air, our body is cooled down. That is a convection process. So this del dot Vu term, this represents this convection process. And this is a diffusion term. This represents the diffusion process that I have already mentioned. This process becomes active when there is a difference of concentration. For example, you have water in a jug, there is a sugar at the bottom of the jug, and after some time you will see this sugar spreads in the whole water, and its concentration is the same everywhere in the water. What made this sugar to spread in the water while it was in the bottom? So that is a diffusion process which made this sugar to spread in the water through molecular action. This diffusion process takes place through molecular action, microscopic phenomena. This is a microscopic phenomena, while convection is a macroscopic phenomena. This is due to bulk motion of the fluid. And plus F, this is a source or symptom. This may also.
Assalamu alaikum, sir. Please, soft reminder. We need to wind up in 2-3 minutes.
How much
For
time?
the next talk, it's 12:23 already.
When
And sir, it started at 11:55.
Okay.
Thank you, sir. Thank you.
We have these five interpretations of this equation. That's why this equation can be used in all other disciplines, and mathematics can be used in multidisciplinary paradigm. Means mathematician will do his own part. For example, measurements, data analysis, and application of formulas for certain calculations. In interdisciplinary paradigm, a mathematician will model physical processes and chemical processes, and will integrate mathematics with the concepts of other situations, other disciplines. And for conducting this research, we need to design a curriculum to support such type of research. We need to redesign our teaching style, our problem-solving style, our collaborative work, and visits of places of application areas. As far as curriculum design is regarded, we need to include some other discipline, like we can have 2 majors in 2 disciplines. We can have 1 major and with 1 minor and 1 distribution area. We may have 1 major with 2 minors. So we need to integrate more than one discipline into one curriculum in order to conduct interdisciplinary research. So I will not go into the detail of these items. How to conduct this research, we have certain steps. If we don't know the background knowledge of other discipline, we cannot interact with that discipline. So we will have to gain knowledge of that. We will have to understand the problem. We will have to model that problem in mathematical terms. We will have to solve it, interpret it, and give the solution to the people of that discipline in their own terms. Okay. That's all from me. With the conclusions, we have the mathematicians have great opportunities to interact with other disciplines because of the abstract nature of mathematics. It can be only mathematics can only be a unifying science, and mathematics graduates have great opportunity for their marketability and employability. Question?
We have
Sure.
possibly
Questions are welcome.
Ji, sir, thank you so much for such a nice talk and explaining the concepts of multidisciplinary, interdisciplinary, and also across the different boundaries of the subjects, and also taking up the strength of mathematics to carry out this work. Sir, we have questions. It's a journal one. It's journal one. Can I please ask from you? They say that can you tell us, as we are from Multan, so which organization, institute, and companies of mathematics they hire maths graduate? It's actually not about your talk, but maybe you can throw some light on it.
Yeah, actually, as we discussed this issue yesterday, we, the mathematics graduates, will have to develop some competency that is needed by the industry. If you remember, Dr. Fiza, we met in Women University, a president of Chamber of Commerce.
Yes, sir. Yes, sir.
Yeah, he told that the university is producing graduates which do not fulfill our needs. So we are teaching our students a curriculum, the skills that are not the need of the market. How can they get employability? So we will have to learn what are the needs of the market, what are the needs of the industry. For this, Dr. Adnan Qasim advised, and I did some exercise that we should explore the industry in Multan, and we should know which. What are their challenges, what are their requirements, what processes they are conducting, and then we will search what are the mathematical models of those processes, how those processes can be improved. When we know their terminology, we know the ways to improve those processes, then we can go and we can talk to them so that we have the skills to improve the quality of your products, and we have this knowledge and these skills. And when they will know that we know their problem, we know their terminology, we can talk to them in their own language, then we will become the need of the industry. Otherwise, in the current situation, we are not the need of the university, the need of the industry. So how will industry spend money on us? So we will have to create our importance. We have to add value in the subject of mathematics, and we have to add the value of our graduates. And obviously, this requires competencies.
So there is another question from Dr. Muhammad Mujtaba Sheikh. He is asking that in our teaching community, we can see only a few one who actually bridge mathematics with other disciplines, especially when teaching to other discipline students. So we won't we need to train all to have similar attitude towards teaching and research?
Yeah, that's important because now currently internationally there is a trend that whatever you do, it should have some impact. So people like to know the outcome. What will be the benefit of your work? But in Pakistan, we are lacking. We are not going with the international community, and so we need to spread awareness. But we have done this in this event. This is an activity to spread awareness among the mathematics community, and we hope that other institutions following us will improve their curriculum. They will include other disciplines. They will teach their graduates. And
एक बच्चा पूछा सेट किड्स इशू होंगे या नहीं होंगे? Sorry sir, sorry to interrupt.
And in this way, obviously, without designing such curriculum, without such training, we cannot expect our graduates to work in multidisciplinary environment. I wanted to give my own example of Indian project. Actually, Indian project is a multidisciplinary project that requires mechanical engineers, that requires physicists, chemists, chemical engineers, skills of engineering softwares, applied and computational mathematics, and CFD and computing facility. All these areas are required for conducting research in this project. We tried to collaborate with the people of these areas, but we didn't receive any response. So we started learning these areas on our own. So this is what we need to do in the prevailing environment in Pakistan that I have mentioned here. Okay, we will have to work consistently. We will have, in the beginning, you may have to face many challenges, but continuous, consistent, and devoted efforts will bear fruit. So if you continue with the missionary zeal and zest, then you can become a multidisciplinary researcher. Otherwise, in the prevailing environment in our institutions, we cannot become a multidisciplinary researcher because the environment does not support, the institution does not support. When you enter into multidisciplinary research, your publications number of publications go down for a number of years. For it may take 3 to 4 to 5 years that you will not be able to publish, and you will have to listen other people. You will have some very bitter remarks from others during this period. But if you work with missionary zeal and you continue with consistency and devotion, ultimately you will succeed. Allah will help you, and then you will be taught bearer of for others. Actually, here everybody can easily move with the wind, along the wind, but it's quite difficult to move against the wind. So far, in order to conduct multidisciplinary research, we will have to we will have to courage to move against the wind. We will have to face all the challenges. Otherwise, we cannot enter into this area. Otherwise, it's a slow process. If we have designed a curriculum, a multidisciplinary curriculum, we will teach our students, we will give them opportunity to learn other disciplines. When they will be graduated, it will be quite easy for them to work in multidisciplinary environment. But in the current situation, it's quite difficult when you haven't experienced or background knowledge of other disciplines.
Thank you so much, sir. Thank you.